Hello, and a warm welcome to the Arrhenius equation and the three uses which are in the data booklet. Okay, we can use this for graphical representation of calculation of activation energy, but we can also use it in a derived form to work out the activation energy without a graph given two different temperatures. So let's start with what's actually in the data booklet. We get the fairly unuseful and looking slightly unfriendly K rate constant is AE, mathematical E, the exponent being minus EA over RT. If we take natural logs of each side, ln K is EA over RT plus ln A. Okay. K is the rate constant, as we know, is only changed by temperature and a catalyst, which changes the activation energy. So if we change the activation energy or the temperature, then we can change the value for K. A is the pre-exponential factor. This is to do with the frequency of collisions. That's your collision theory, which we know and love. EA, activation energy. You should have a good grasp of that before you go further into this video. And then R times T is universal gas constant times temperature in Kelvin, not forgetting that R times T is basically the average kinetic energy. So what the Arrhenius equation allows us to do is to relate the ratio of the activation energy to the average kinetic energy. So basically the higher that ratio, the slower the rate, because it's an exponent. Okay. So how do we get from the first given equation, the K is AE to the minus EA over RT, now I've discussed those variables, to the natural logarithmic form? Well, take logs of both sides, so K becomes ln K, then the right hand side is ln AE to the exponent minus EA over RT, slowly drag out each of the quantities from the bracket, and then we end up with minus EA over R is 1 over T1 plus ln 1 over t. I'm just going to be ahead of myself on the video there. Okay, so then we've gone from the original equation down to the derived equation, which is much more useful for us as chemists. Why is this useful? Well, we can use it as this form, as y equals mx plus c, in a wonderful experiment, perhaps even an internal assessment. Because the y-axis is the natural log of k. We can work out k from experimentation. The intercept will be ln A. So if we take e to the power, whatever that value is, we get the a, the pre-exponential factor. The gradient is minus EA over R, times it by 8.314. You have the activation energy plotted against x, 1 over t. Okay, so now we have our Arrhenius form in a useful form, and this is actually in the data booklet in this manner. Just double checking. Yes, it is. I've just expanded the 1 over t to show clearly where x is, which you need to plot. They often give you the temperature in degrees C, change it to Kelvin, or they might even give you it in Kelvin, and then you just have to take the reciprocal of that and then tabulate it. Sometimes they give you those and expect you to plot the graph from there. Well, those are the two probable ways that the IB could ask this question. Okay, so to calculate the activation energy without a graph, we need to go to the third equation, which looks slightly unfriendly. Okay, we know that the Arrhenius plot is a straight line, and because it's a straight line and it's of the form y equals mx plus c, we know that any two values will give us the gradient of that line, which is going to give us the activation energy. So if we run the experiment, we have data at two different temperatures. We only need those two different temperatures for us to actually calculate the activation energy. And this is where the third equation comes in. So now we're using the ln K1 over K2, the ratio of the two rate constants, is going to be EA over R, activation energy divided by the universal gas constant, and then the difference between the reciprocal of the two temperatures. Where does this come from? Well, ln K2 minus ln K1 is going to be ln A minus EA over RT2, and times by ln A minus EA over RT1. The derivation is not needed, nor will it be asked by the IB, and you can see that I'm struggling to actually get my closed bracket on the right hand side. That's just there for your interest as interested students, keener to understand where the actual science comes. And let's not forget, mathematics is the language of chemistry, so it's important, I think, as a teacher, that my students understand where this actually is derived from. So we end up with this, and we've got two different temperatures, no graph is needed, and we can work out the activation energy. Subsequent videos will give examples of this.